So tangent inverse or arctangent is the inverse of tangent x. So what does it mean? It means y equals tangent inverse x means tangent y equals to x. So what I'm saying is, if you start with x, you do tangent inverse of it. You're going to get y, which is tangent inverse of x. And that's your undoing of tangent of function. In this case, tangent y. Okay? So we're undoing each other. If from here to here you got by doing tangent, and to go back, you want to go tangent inverse. If from here to here you're going to get by tangent inverse, then go back by tangent. So undo. That's exactly what we're doing. Okay, so now if you look what is here, this expression. So what it basically says, it says tangent, you recall what y is tangent inverse of x, that equals to x. So that's what you're going to be using when you're going to be taking the derivative. So let's now take the derivative. So you want to find derivative tangent inverse. We'll do exactly the same steps as we did for the derivative of sine inverse or derivative of ln. We start with named equation. So y equals to tangent inverse x. Next step, we want to get rid of a function we don't know how to deal with. We want to get rid of tangent inverse. So what we'll do, we're going to take tangent of both sides. Then on the right side, tangent of tangent inverse, we're going to be canceling each other. We have just x. On the right side. Left side is tangent y. And at this point, we're going to take the derivative of both sides. Derivative of right is easy as 1. Derivative of left is, derivative of tangent is secant squared. Keep argument y times y prime, because we're doing chain rule. Derivative of implicit function. Solve for y prime, 1 over secant squared. Do back substitution, because you recall that y equals to tangent inverse of x. So derivative of tangent inverse of x equals to 1 over secant squared of tangent inverse of x. And now what is left is to massage that expression a little bit and simplify it. And that's what we're going to be doing. What we wish instead of that secant function, which is we have here, we wish to have tangent, because if it were tangent of tangent inverse, it will just disappear. So let's see how we can express secant in terms of tangent. So I'll do it somewhere on the side. Again, recall the main trig identity. Sine squared plus cosine squared equals to 1. Because we want to have secant and tangent, to get secant and tangent, we're going to divide both sides by cosine squared. So everything divided by cosine squared. Then 1 over cosine squared on the right side is secant squared. Sine squared over cosine squared is tangent squared. And cosine squared over cosine squared is 1. So what we've got is secant squared equals to tangent squared plus 1. And now we'll calculate secant squared of tangent inverse x. So instead of x here, I'm putting tangent inverse. So then my left side is going to be equal to tangent of tangent inverse x squared plus 1. The good thing about this expression is that is x because of square is x squared. So what is happening at the end is the following. Derivative of tangent inverse x is 1 over 1 plus x squared. Nice formula for derivative of tangent inverse. Same way if we take derivative of cotangent inverse, it's still going to be 1 plus x squared. The only difference is going to be minus. So it's going to be exactly the same calculations we just did. Only difference is going to be because we're going to be taking derivative of cotangent somewhere here when we are at this step. Derivative of tangent is minus cosecant squared, so we'll have extra minus secant somewhere. That's the only difference. Otherwise, calculation will be extremely very similar. Right? So what's derivative of tangent and derivative of cotangent? And from here, we can get antiderivative of 1 plus x squared. It's going to be equal to tangent inverse of x. To derive a shortcut formula, for integral, what we'll do is we'll take the derivative of, say, tangent inverse of x over 3. Same way as before we did derivative of sine inverse of x over 2. Here we'll do tangent inverse of x over 3, which will kind of lead us to for a formula of what will be tangent inverse of x over a formula. And that somehow will lead us to a shortcut for integral formula as well. Minutes to calculate the first derivative, and then we'll kind of discuss how to get this second derivative. So that working. Chain rule, derivative inside function, derivative outside. Derivative inside is 1/3. Derivative of tangent inverse is 1 over 1 plus x over 3 squared. So that is 1/3. 1 over 1 plus x squared over 9. And what we have here is we have complex fractions. Usually we don't want to have complex fractions. So what we'll do is we want to get rid of it. What makes that complex fraction is that extra 9 on the bottom of x squared. So we'll have to take care of that 9. So we will take care of it by multiplying bottom by 9. If we multiply bottom by 9, we have to do the same to the top. And bring 9 inside. So we're going to have 9, 3, 9 plus x squared, reduce. So we're going to get 3 over 9 plus x squared. So can you guess what we're supposed to have? The second derivative.
A over a squared plus x squared.
A squared plus x squared, and on top?
A.
A, perfect. Now, can you guess what will be antiderivative of dx over a squared plus x squared?
Plus c.
What else is missing? You see 1 over a in front because we need to have a on top, right? So what you kind of mentally do, you put a here and 1 over a here, right?
Yeah.
So then that expression becomes tangent inverse of x over a, and you will still have that extra 1 over a. Okay? That will be our shortcut.